we're getting into our problem-solving discussion. And this should be a little bit easier to get through because now we don't need to talk about specific brain areas or too much else. We are going to talk a little bit about some of the logic behind how we logic our way through things. So one of the things when we're looking at how we make decisions, one of our theories is called rational choice theory. And this says that we're going to be making decisions by determining how likely something is to happen, judging the value of the outcome, and then multiplying the two. Basically, we're going to say, I'm going to decide if I do this or don't do this based on how likely I think that event is and how much I want that event. You're going to be looking at sort of the likelihood, the odds of something occurring, if that is good or bad, and how strongly good or bad it is. And then you're going to make your decision based on sort of the product of that. Now, we could go into specifics of models, but I never do that. Instead, we're going to say, okay, based on that general description, what are some potential issues? The first of which is the fact that people are fairly good at estimating the frequency of an event, how often it occurs, but we're actually really terrible at estimating probabilities. And this seems really weird because you're like, well, frequency and probability go hand in hand. If you've taken math courses, it's pretty easy to calculate out, looking at sort of occurrences, number of occurrences across time, and then we'd say what are the odds of it happening in the next instance. We could make a decent estimate from the numbers. But if you just ask people to make sort of a gut response, we are okay with frequencies, especially frequencies that we can talk about in terms of our past experiences. Oh yeah, this tends to happen once every 5 years, 10 years, whatever. But if we said, okay, what are the odds of that happening in the next year? We can't do that. We don't think to put things into numbers and do the math. We make a guess, and we tend to be very inaccurate in those guesses. And there's lots and lots of cool studies. They'll do things like, one of the ones I think of from one of my other classes, we talk about a bunch of, say, Harvard graduates, because of course that's who you ask if you want to make a point about sort of human logic being fallible. And they'll ask them the probabilities of certain things and find that their performance is far below even what we would expect at chance levels of guessing for a bunch of different logic problems. And it just goes to show that if we're not doing things mathematically, we tend not to think in mathematical logic. So that means that this rational choice theory doesn't always work, especially if something isn't framed in terms of frequency estimates. As soon as it's worded in a slightly different way, our performance will drop dramatically. So we're definitely going to find that our performance varies depending on how this problem is described. So what are we going to call that? We'll call those framing effects. So this means that people are going to give different answers to what is effectively the same problem, just depending on how we phrase or frame that problem in the question. But we're basically looking at things framed as either a gain or a loss. So here we're looking at a disease that's running rampant on some alien planet. Actually, I think it's just Mars. But we're saying, all right, if we frame it as a gain, we're saying that you can give this new treatment and you have the odds of saving this many people, or you have sort of these even odds that this many people will be saved and this many people will die. And then we do the exact same question, the exact same odds if we work it out numerically, but it's framed as a loss, where we're saying you have these odds of this many people dying. And it's always framed in terms of those losses. And what we find is that even though the math is identical, even though it's exactly the same, we find that if it's framed as a gain, people tend to choose to sort of go with this option here. We tend to find that they're going to try and try and save individuals. And then at the bottom here, we sort of see the opposite. We'll actually find that you tend to be a little bit more risky in order to try and avoid losses. So gain versus loss, we often end up with opposing choices because we'd rather a sure thing in terms of wins, and we would rather gamble to try and have no losses in that loss framework. And while this is framed here as you're making decisions about saving or losing lives, you can actually frame this in terms of gains or losses for, say, gambling. And the reason I think of this is that one of the labs at the U of A, actually, I think they just retired. But if you get to look into Marcia Spetch, Dr. Spetch did a bunch of work on gambling in humans as well as pigeons, which seems really, really weird, but pigeons are actually a fantastic model of human gambling behavior. And she has a bunch of really neat research that actually evaluated different things that affect risky choices, making decisions for risks, like in this loss framework, and different factors that can actually influence that. And finding things like having ambiguity. So here we're explicitly stating our odds. While that can sort of improve our sort of guesses, we do still find that bias exists. But if you do something like forcing people to figure out those odds from experience, we actually tend to overweight our wins and we tend to underweight our losses. So we end up with even extra bias in those cases too. So we think about wins and losses or gains and losses in very, very different frameworks. So if it's something you're curious about, Dr. Spetch's research is a very good spot to start. So if that has sort of explained that humans make very irrational decisions, so our rational theory of decision making is probably not what's actually happening most of the time, let's look at a couple of different things that tie to this irrationality. What is it that makes us make the decisions that we do? And I will state that while this is going to be a lot of here's how we make mistakes, I would stress that in a lot of cases, some of these biases exist because they can be functional under certain conditions. Oftentimes, if you look at certain actions that seem sort of counterintuitive, you could say, well, how would this work in, say, a small group setting or a more naturalistic setting where human behavior would have started evolving? That might help explain some of these. But I'll sort of try and keep that explanation to a minimum. Just know there are entire classes on that as well. First thing though, prospect theory. So this is pointing out that people choose to take on risks when we're evaluating potential losses, and we tend to avoid risks when evaluating potential gains. So another way of saying what I just did with our Mars example, but with a proper name, prospect theory. But this is when you take the certain thing for gains and you are risky, you take on risks or gamble a little bit when there's the potential for losses. So we would much rather gamble to not lose anything, even if the odds aren't good. But if we are trying to gain stuff, rather than gambling, trying to win more, even if there's a risk of getting nothing, versus taking a sure thing, we're actually going to take the sure thing. So it's kind of weird that we'll do the opposite. So next we have our sort of quick and dirty methods versus slow and steady methods for evaluating what responses we should give. This is another one of those, there's a potential trade-off. So the first is using a heuristic. So this is that quick and dirty method. This is sort of like a fast solution. So they tend to be our shortcut rules that we're going to apply to try and solve problems. Now, we look at this and say, oh man, we see it as a quick and dirty solution, something that's maybe not guaranteed to give us a solution if we're looking at the bottom, but it's fast. Usually we'd say, well, that's bad. But if you think about it, a lot of times we encounter very similar situations over and over and over again. So if you encounter a problem and you have this gut response that I should react this particular way, oftentimes, if it's something that's helped you before, doing so more often than not is going to help you out. The thing that keeps popping into my mind is navigating. I'm not great going off of my beaten path. I tend to follow the same routes because it's nice and predictable. I know the traffic patterns, it's great. But it is also Edmonton and construction pops up at odd times. So maybe you're encountering a sudden my lane ends or a sudden I want to turn a certain way but I can't. You might have certain strategies that have been really useful to help you, say, merge quickly and safely. You might have strategies of maybe there's a quick way to detour around this area, and I'm just going to follow my gut. I don't know if it's the fastest way to detour, but it's something that's worked before. So you can frame heuristics as, yeah, it isn't something that we're thinking through in a lot of detail, but oftentimes it can be fairly useful. Now, if we want to guarantee ourselves a solution, rather than hoping that something has helped us out because it's worked in the past, you could go with something more slow and steady, which would be an algorithm. And here we're saying that we have, say, a well-defined sequence of different procedures or rules, a logical sequence of events that we're going to undertake to guarantee a solution to a problem. So we have step-by-step attempts. We're going to try everything until we finally find a solution. And we're doing it in a systematic way so that we ensure that we arrive at a solution. A fantastic example for both is trying to unlock, say, somebody's computer. So you know that you have somebody's computer and there is a 6-number sequence that you need to type in to unlock their computer. If we were going with an algorithm, we'd start with the number 1. So you'd go 1, 1, 1, 1, 1, 1. That didn't work. Okay, 1, 1, 1, 1, 1, 2, and so on. You are guaranteed to get the right number eventually. It's not going to be quick, but you are guaranteed to get there at some point. In contrast, a heuristic would be something like, well, I know this person, so let's try their birth date. Let's try their sister's birthday. Let's try their partner's birthday. So you can run through things that logically make sense. These are numbers kind of at random, so not following our strategy at the bottom where you're guaranteed to get there, but if they happen to use a number that makes sense to them, then you're probably going to find it a lot faster than by the time you get there from, your 6 digits cycling through 9 possibilities each. That is an awful lot of possibilities. So in those cases, your heuristics might be the better bet. And of course, we have different types of each of these. So we're going to focus on the heuristics. The first is the availability heuristic. And this is the fact that we tend to estimate frequencies of events based on how hard or easy it is to think of them. So stuff that's easier to call to mind, we assume it occurs more frequently. One of the issues here, once again, is that different stuff is going to stick out in our minds for different reasons. Something innocuous like, say there's a newspaper article that reports these statistics on heart attacks. That tends not to be overly attention grabbing. But if there's a massive article that's talking about the most recent surge in shark attacks, where there have been, say, 2 in a span, which is a 200% increase over the last year, well, all of a sudden that seems like a really big risk and something that happens fairly often. The standard example is they talk about death by vending machine versus death by shark, and one is significantly more likely to occur than the other, and I will tell you it is never the sharks to blame. Same thing goes with cows. You don't think of cows as being overly dangerous, but we domesticate an awful lot of cows, and so there are a lot of bovine-related deaths across North America and very, very few shark-related deaths. But, of course, shark attacks stick out in people's minds, so we overestimate how likely they are to occur. So stuff pops into our minds very, very quickly, and we just assume it's fairly common. I also use the example here. When you're driving somewhere and you get to your destination and you're like, oh my God, I hit every single red light between here and there. And maybe that was true, or maybe those red lights were just more distinctive because you had to sit there and stare at the red. Whereas the greens you got to drive through and didn't pay attention to. I, having taught this often enough, start counting how many lights I have to drive through, and I actually think about it. How many did I actually stop at? It's not very many most times, even if I was frustrated about how many I had to stop at. And that's all about that distinctiveness in your memory and our over-representations. We can also talk about our representativeness or a representative heuristic. I've seen it both ways. This is when our problem solver, the person encountering a problem, is going to mentally compare something to a stored prototype of an event, object, or person, tying in with some of our categorization. So we can make some assumptions saying, hey, this seems to belong to this category. I should approach it the same way that I would anything within that category. And again, it might be useful, but it also might not be useful. So if you have misidentified something as belonging to a category, hey, I've seen this type of problem before. I definitely know how to solve it. Let me just sort of go through the steps that have worked in the past that might actually distract you from finding the real answer if it isn't actually the same kind of problem you're thinking of. So in this case, while, yeah, we could determine something falls into a category, and if it really does, that's super useful. But if it doesn't, we've now sort of set ourselves up to be looking in the wrong place. And a lot of these, we can think of times when, yeah, it might be useful for stuff to fall into a category and go with it. Or even our availability heuristic, just thinking about sort of when was the last time I did this thing? If it's easy to think of, then I've done it recently. That can help sometimes, but not always. Another sort of set of things to talk about are our logical fallacies. And these are just sort of inherent issues with how people tend to think. So the first is the conjunction fallacy. And this is the fact that people are more likely to think that two events, they are more likely to occur together than they are to occur separately. So the standard example, I've seen this phrased in a bunch of different ways. Every textbook uses basically the same thing, but we'll say, okay, I'm going to ask you which of these is most likely. So we know that Linda is a bank teller. She might be a feminist. She might write poetry. Maybe she is a poetry writing feminist bank teller. And people would say, okay, based on some of these qualities you've described, they all fit together. So it's likely that all of them are true. But if we go into probability, if you go into sort of our mathematical considerations, the more things that have to overlap, that have to co-occur, the less and less likely something is. So if I tell you that we have two individuals and one is a bank teller and one is not a bank teller, you have sort of 50-50 odds of getting it right. If I tell you then that one is a bank teller and the other is not, and one is a feminist and the other is not, we're now in, again, 50-50 odds for each. But if we then say, what are the odds of this one person being both the bank teller and the feminist, we are now at 25% odds, keeping the numbers nice and simple. So the more things that need to co-occur, the smaller and smaller that likelihood is. But because they get more and more specific, the more things that are co-occurring, people assume that that descriptor is getting more and more accurate and therefore is more likely. So regardless of how they frame these types of questions, people tend to estimate that those co-occurrences make something more likely rather than less likely. So as per usual, people are really bad with going through probabilities. We're a lot better at those frequency estimates, but probability really throws us. And this is a fantastic example of that. Another of our logical fallacies is something you're probably familiar with, and this is our sunk cost fallacy. And in this case, people make their decisions about a current situation based on what they have already invested in that situation. So you've been sitting at the bus stop, and the bus is supposed to come every 15 minutes. And you've been there for 35 minutes. And you're at the point of, okay, well, I could try a different bus. I could just walk. I could grab a cab. But it comes every 15 minutes, and it's been more than 15 minutes, so I'm sure as soon as I walk away, it's going to come. So I'll give it another 5 minutes. At that point, maybe you need to wonder if there's something up with the buses rather than staying and persisting. So that would be an instance where you've given in to that sunk cost fallacy. This can also relate to another fallacy called the gambler's fallacy. And that's when we usually think of it in terms of gamblers, where they assume that because, I've had 100 pulls of a slot machine and I haven't won anything, so my next one must be the one that's going to pay off. But if we think of the probabilities in terms of gambling and slot machines, every single pull has the same odds. You have, say, a 1 in 1,000 chance of something happening, or whatever our value is. And so whether you've had 100 instances before that with no prize, or you just got a prize, every single pull has equal odds. So the gambler's fallacy would mean that you shouldn't actually take into account all of those previous exposures because the odds are consistent. But we have that fallacy, that feeling that, oh, I must be getting close. So that's another one of these fallacies. And again, just sort of the way that people think about stuff, we tend to sort of frame things not quite accurately. From that, we kind of got the idea that humans, when we're considering information and using that information to make decisions, we have sort of biases in the way that we think. And when we talk about bias, that's something huge in psychology. And of course, they've named all sorts of different kinds of bias. So that's the next little chunk here is some of those named biases in our decision-making process. So the first of these is the confirmation bias. And this doesn't just apply to problem solving, this applies to a bunch of stuff, but people don't like to be wrong. And what we'll do is we actually overweight information that matches what we already believe. And we will underweight and ignore information that goes against what we believe. So if you're having a debate with somebody, maybe you're talking about somebody being a fantastic actor or they hate that actor. If you're Googling to find something that's going to support your argument, you're probably going to search something like actor or reasons why blank is the best actor or something like that. So you are actively seeking out information that matches what you are trying to argue, what you already believe. And the other person would probably search for something similar, but why they're the worst actor, something that matches their beliefs. And this is something that can happen intentionally, so searching for stuff that matches, but it can also be things like they've done studies where maybe they get participants to read a very persuasive article. So we've argued to persuade you to have a specific belief or stance on a topic, and then we're going to give you a stack of different articles and see which ones you read. And people will often skip over ones that seem to explicitly disagree with whatever we've told them is the correct stance. And they will spend more time on the articles that match their current stance. And this has been done in a bunch of different ways, and people do this whether we're aware of it or not, hence it being a bias. So we overweight stuff that matches, we underweight stuff that doesn't. Sometimes we actively seek stuff that matches while ignoring stuff that doesn't. And of course, that's going to influence the information we're using to make our decisions, to form our opinions. So that's something important. And I believe it comes up a couple of times this semester because it'll also be relevant in social behavior because we can pay attention to behaviors that match expectations while ignoring those that don't. So this applies at multiple levels. We also have something called the optimism bias. And this is something where people believe that in comparison to other individuals, they are more likely to experience positive events and less likely to experience negative events in the future. This, of course, will be modulated by a bunch of different things. So we'll start seeing that when it comes to sort of forward thinking, if we say look at individuals with depression, they would have an opposite framework here. And that'll also apply to some of our social behaviors and also attributions, which will come up in a later chapter, where once again, individuals with depression will have a much more negative framework. But on average, people are going to be a lot more sort of optimistic about what's coming in the future. They assume that good things are just over the horizon, and so they might make decisions sort of with that hope that things are going to get better. So rather than trying to sort of match their decisions to their current state, they might try and make it match what they think is going to come in the future. So maybe they decide to spend a little bit more now than they should because, well, they're definitely due to get a raise sometime in the future. So little biases in how we think. We also have our belief bias. This is when we're making judgments about whether to accept conclusions. It's going to depend a lot more on how believable the conclusions are rather than whether those arguments are logically valid. This is a weird one, and the wording for it doesn't necessarily help, but this is basically saying that if we give you a logic statement, if we give you an if-then statement, and we talked about these when we talked about our methods. And so we talked a hypothesis is going to be a logical if-then statement, where we'd say if this theory that we're basing our experiment on is true, then we would expect this type of behavior. So if we make a large logical argument where we're stating that, maybe something is true, or under these conditions, this thing will be true. If we've made a claim, if we've made one of those logical statements that goes against what we know in the real world, it actually creates conflict, and people have a lot of difficulty following those logical statements if it goes against what they know is correct. So one of the examples in one of the standard studies they'll do is they'll say, okay, if smoked chemicals are good for us, then cigarettes are healthy. And people would be very likely to disagree with that, even though we've made this statement that smoked things are good for us. That is our statement, that is our sort of claim. And then from that, knowing that anything that is smoked is healthy, we would expand that and apply it to another statement. But because we know from research that cigarettes are not healthy, people would disagree with that, even if following the logic, we should say, yes, that is true according to the rules that we've set. So we don't like stuff that goes against our internal understanding of what is true, even if we're told sort of suspend what you know and just focus on the logic of the moment. We don't do well at that. So this is tied into something called syllogistic reasoning, which is basically when we're trying to determine whether a conclusion follows from two statements that we are assuming to be true. So that's the cigarette example, but with the proper terms for it. And what we care about here is the fact that we have a hard time separating sort of raw logic. So we've given you statements that we're telling you are true versus knowledge that we've acquired from the real world. If we put them in conflict, we rely a lot more on our internal beliefs rather than on something that we've been told to follow as true logic. And that's another one of those weird quirks of human behavior. What else do we have here? So getting into means ends problem solving, or a means ends analysis. This is one of our methods of trying to find a solution to a problem. So this, rather than something like an algorithm where we start with sort of our systematic steps, so our 1, 1, 1, 1, 1, 2, and so on, here, we're actually keeping it a little bit more vague and saying that we're going to look at our end goal, keeping that in mind. So we have our final goal state of what does it mean to solve this problem. So that is our ends. And we want to look at the means or the steps that would help us reduce the space between where we're starting and where we want to be. So if we were looking at, I don't even know if I have the image here. There's one of these standard logic problems. It's called the Tower of Hanoi, but I didn't know that. It's one of those, you have your 3 pegs and you have a bunch of those donut shapes that are larger or smaller, and they'll stack a bunch of them on one side, and you have the rules of, I need you to move all of these donut shapes to the far side, to the opposite side from where you've started, but you can't place a larger ring on top of a smaller ring. So how can you shuffle them over so that the largest ring is on the bottom and the smallest ring is on the top on the far side? So if you aren't familiar with that, you can look them up because you have the name now. But it's just sort of a standard, can you go from your start point to your end state? And sometimes you don't necessarily know all the exact steps, but you'd say, okay, well, in order to be able to sort of get to that final stage, I'd have to have the largest one on the bottom first. So how can I move stuff to get the largest one on the bottom? Okay, now that we've done that, what's the next step? What do we have to do next? So if we wanted to break it down, we're going to look at what is that end state? Where are we starting? And how do we sort of break it down to get to that final solution? So this is kept very vague because we're saying, well, look at our end state, look at the goal, look at our current state, look where we've started, and then how do we get from A to B? So I use my specific example because that is way easier to visualize than something vague, but you can apply this to a bunch of different scenarios. You could even use this for something like studying. So you want to be able to be prepared by the exam on Friday, and to get to that end point of having all of this knowledge ready, maybe you have to break it down. I need to study chapter 2 today, and then I'll study chapter 9 tomorrow, and so on, you could break things down accordingly, and it would technically fit this. And then at the bottom here, we're talking about sort of some of our ways that we could sort of break these lists down. So how can we sort of make those gaps smaller, get us closer and closer to that end goal? They talk about a couple of different things, generating your sub goals and stuff like that. But because we're rushing through this, we're not going to care about those details. We're just saying end means is we care about the start and the end and forming steps between. That's sufficient for us. Next, we get into analogical problem solving. And here, we're trying to find a similar problem that we've encountered before that has a known solution where we could apply that solution to some current problem. Now, sometimes you'll have a direct comparison. So I've seen exactly this kind of logic problem before. This solution worked last time, so I'm going to use that exact same solution. And if they are actually the same, then that's a fantastic way to quickly find a solution based on that past experience. So we're going to find that if you've encountered a similar problem before in different experimental designs, we actually find it facilitates problem solving on subsequent exposures to similar types of problems. And this is versus someone who has been shown this type of problem for the first time. The second time or the third time is going to go a lot faster than that first time. And that brings us to a related concept called a mental set. So once we've encountered a type of problem and we have that understanding of this is the kind of solution, these are the steps I'd need to take in order to solve this type of problem, we've now formed a mental set that includes that expectation that these are the steps to take. Now, I have an example, and I've seen this in a couple of different textbooks. This image is one of the best, so I keep it. But in this case, you can read through them and go into more detail if you are curious. But basically, we have this target cup, and our goal is to get 100 ounces of water into this cup. It's from a different text, so it's in ounces instead of something useful like milliliters. But we have these options. So we have an unlimited supply of water, and we have to do something to get 100 ounces. So I would say right off the bat, let's dump cup A into our target cup, and then we will take away 1 cup of B and 2 cups of C. So A plus 2 of C would be taking away 27, which would get us exactly 100 ounces. So we can find that solution. And I find it very quickly because I've used this example repeatedly over the years. It might take other people a little bit longer. But now that I've told you the solution, if I switch to the next problem and I say, hey, once again, we're going to be using 3 different cups, unlimited water. Now our goal is to get 20 ounces. And we look at it and go, oh, okay, well, A and then B taking away and then take away 2C actually, I think gets us the same solution. I'm not going to try and do the math once again, but I think the logic is the exact same solution works. However, you might not have considered the fact that if we actually just add B and take away C, we found the solution much faster. And when you conduct this type of a logical experiment, and half of our participants get problem A, then problem B, when solving B, they will use the same solution as A. They got stuck with a mental set, and yes, they found a solution, but it was way more steps. If you're presented with B first and then A, then you're more likely to find that faster, more efficient solution because you don't have that preconception of what steps to take because of that earlier problem. So if you wanted to read through those, the questions are at the bottom, but it nicely illustrates how having a mental set can almost trip you up if it isn't the most efficient solution. So again, sort of like a heuristic where you have a quick and easy solution based on experience, but it's not necessarily the most efficient solution, and it might not even work every single time. So it might not have worked out that they're both identical in solutions, but our point here is that it sort of biased us to avoid a simpler solution. So yeah, these mental sets end up influencing how we approach new problems based on expectations that came from prior experiences. And we've focused on that fact of this could give us inefficient solutions, and we can call that inefficient focus fixation. So we can narrow our ability to think of novel solutions because we are stuck or fixated on those existing mental sets. So all sorts of related terms here. And with that fixation, that ties very nicely into our concept, our last concept of functional fixedness. And this is when we have a preconception about some object or thing functioning in a particular way. So we often view an object as having only one function, and that is the one that we mostly use it for. This, as a real world example, would be something like I have a terrible time remembering where I have put tools. I live in a small space. It should be very easy to find things, but I lose them. I turn up everywhere. But I was trying to hang pictures and I didn't have my hammer, could not find it, nothing was working. And so it's like, okay, maybe I just can't hang pictures. But then you have a moment of, well, anything that's strong enough to not dent when you hit it against a nail is going to put a nail into drywall. I'm not hanging anything heavy. So I went and I grabbed something I didn't care too much about that was fairly heavy. I think I used my stapler and I knocked my nail into the wall, and it's like, perfect, that was a solution. But I spent an awfully long time searching for a hammer because you're putting a nail in the wall. That is a hammer job. So you get stuck with that function based on sort of what purpose it serves, and you can actually miss easier solutions and sometimes more efficient solutions because of that. Another example is the standard one. Again, I've seen multiple textbooks use the same basic idea here. And what they do is they give people this box full of things. So we have our box, we have a candle, we have our push pins, and then we have a mat. And they tell you, we want you to somehow get this candle sort of standing upright and positioned in a way that it's not going to drip on the table. And so people will usually take everything out and they're going to start using push pins to try and say, pin this candle up to a bulletin board nearby or something like that. But you technically weren't told that you can't use the box. If we give people the box holding all of the items, they assume that the box is a container meant to hold the stuff and not necessarily part of the things that they can use to solve the problem. Whereas if you give them the stuff and the box all laid out separately, the easy solution is just you stand the candle up in the box and now you're done. But presented with everything in this format, you tend not to find that solution. So in these cases, you've gotten stuck that the box is a container, not a prop as part of an experiment, even if it wasn't explicitly stated as such. And there's all sorts of cool examples of this. You can look up functional fixedness if you are curious. But that gets us to the end of chapter 9.